Welcome to the buffers video. By the end of this video, you should understand what a buffer system is and what it does. You should be able to use the Henderson-Hasselbalch equation to calculate pH of a buffer system. You should be able to make predictions about the buffer capacity of a system, and you should understand how to make a buffer system. So let's start by defining what a buffer is. A buffer is a solution that resists changes in the pH when small quantities of an acid or base are added to it. In other words, it's a solution that when you add acid or base to it, it maintains the same pH. A buffer solution contains a weak acid and its conjugate base. For instance, HF, the weak acid, and its conjugate base, F-. Or it can contain a weak base and its conjugate acid. For example, the weak base NH3 and its conjugate acid NH4+. You can also achieve these combinations by combining an acid or base and its salt. For instance, HF and NaF, which is really F-, and NH3 and NH4Cl, which is really NH4+ in solution. A common example of a buffer system is your blood plasma. Your blood plasma contains carbonic acid and its conjugate, HCO3-. This combination of the weak acid and its conjugate base allows your blood plasma to maintain a pH of about 7.35 to 7.45, which is really important. In order to understand how buffer systems work, the Henderson-Hasselbalch equation is going to be really important. This is on your equation sheet. It's worth writing down right now because we're going to reference it frequently throughout this video. You can derive this equation from the K expression. I'm not going to show that derivation here, but you could definitely work this out on your own. So let's think about how buffers work. Notice I've put the Henderson-Hasselbalch equation up here in the corner because, like I said, we're going to continue to reference it. Let's consider this buffer system. This buffer system is a solution of the weak acid HF and its conjugate base F-. Now imagine we add some base to that system. If we add base to this system here, we're essentially adding OH-. That OH- will need to be consumed in order to keep the pH constant. So what can consume the OH-? Which of these two components is able to consume the OH-? Well, the acid component can react with or consume that OH-, according to the equation shown here. So in other words, the acid component of the buffer system steps in to neutralize the added base. Let's consider the opposite. If we add acid to this system, we're essentially adding H+. That H+ will need to be consumed. So which component is able to do that? The conjugate base component, the F- component of the buffer system, can react with or consume that F-. In each of those cases, the ratio of conjugate base to weak acid will be affected. Thinking about this mathematically, if the magnitudes of A- and HA are really large, shifting them by a tiny bit is not going to affect the mathematical value of that ratio. Therefore, the pH won't change. Again, if we consider the buffer system as shown as an equilibrium system here, when we add OH-, we're going to consume some HF and produce some F-. Likewise, if we add H+, we're going to consume some F- and produce some HF. However, in either case, if the amounts are small, the shifts will be small, and the mathematical value of that ratio will remain relatively constant. Here's a visual representation of this same concept. Here's our initial buffer system in the middle, where the concentration of weak acid and its conjugate base are roughly equal. Now, if we add base, that base will react with the HF to produce some F-, therefore increasing the F- and decreasing the HF. And if we add acid, we'll increase the HF and decrease the F-. But again, if these shifts are small as compared to the magnitude of the amounts, the pH change will be negligible. Now let's think a little bit about the properties of a buffer system. Remember, a buffer system is meant to maintain a particular pH, so determining the pH of a buffer system is going to be vital. Recall that the Henderson-Hasselbalch equation tells us that the pH will equal the pKa of the acid as long as this ratio equals 1. Recall that if you take the log of 1, you get 0, so this drops out of the equation and the pH equals the pKa. So in other words, when the concentration of weak acid and its conjugate base are equal, the pH will equal the pKa. The other important property of buffers is the capacity. The capacity describes how much acid or base the buffer can handle before the pH changes significantly. The capacity is determined by the amount of A- and HA, by the magnitude of these values. Recall that the less that ratio shifts, the less the pH will change. Therefore, the larger the magnitude, the higher the capacity. To help illustrate this point, let's consider some baby numbers. Imagine you start with 10 A- and 10 HAs. Let's shift this ratio by 1 so that you have 9 A- and 11 HAs. That's a fairly significant change relative to the amounts. However, now let's consider, instead of starting with 10 and 10, we start with 1,000 and 1,000. Now imagine we shift this ratio by 1, giving us 999 A- and 1,001 HAs. Relative to the initial amounts, this shift is much less significant. Therefore, the larger the magnitude of A- and HA, the larger the capacity of the buffer system. Now let's think a little bit more mathematically about buffer systems. Here we're asked to calculate the pH of a buffer system that was made by combining the weak base NH3 with its conjugate acid NH4+. Notice the NH4+ is written here as its salt, but the Cl- is a spectator ion, so we can ignore it in this case. So of course we're going to use our Henderson-Hasselbalch equation. However, you should note right off the bat we hit a bit of a snag because the Henderson-Hasselbalch equation uses the pKa, and we're given the Kb of the base in this buffer system. It is possible to rewrite the Henderson-Hasselbalch equation in terms of bases, but I think it's easier and also good practice to convert our Kb to a Ka. So recall that Kw is equal to Ka times Kb. Kw at 25 degrees Celsius is 1.0 times 10 to the negative 14th, and therefore that's going to be equal to our Ka times our Kb, which in this case is 1.8 times 10 to the negative 5th. Doing this math, we find that the Ka is equal to 5.6 times 10 to the negative 10th. So that's what we're going to use here. Recall, in order to find the pKa of that, we take the negative log of that value, and we find that our pKa is 9.25. From there, we plug in our A- concentration and our HA concentration, in other words, our NH3 concentration and our NH4+ concentration, and we solve to find that the pH is 9.04. A couple of things to note about this example. First, the pH is not equal to the pKa because the concentrations of A- and HA are not equal. Therefore, we're not taking the log of 1. We're taking the log of a value smaller than 1. Thinking more generally, when A- is less than HA, we'll always end up with a pH that's less than the pKa because you're taking the log of a number that's less than 1, which will give you a negative value. So you'll be subtracting from the pKa. On the other hand, when A- is greater than HA, you're always going to end up with a value where the pH is greater than the pKa because you're taking the log of a number greater than 1, which will give you a positive value, so you'll be adding to the pKa. Now let's look at buffer capacity. Recall, buffer capacity is determined by the amounts of HA and A- in solution. As we mentioned before, the larger the magnitudes of weak acid and conjugate base in the buffer system, the larger the buffer capacity. To illustrate this point, we're going to compare what happens when small amounts of gaseous HCl are added to a buffer that has large amounts of weak acid and conjugate base, and then what happens when it's added to when that same amount of acid is added to a buffer system with smaller amounts of weak acid and conjugate base. So let's start with solution A. That's the one with the larger magnitudes of weak acid and conjugate base. In this case, again, we're ignoring the Na plus and considering our CH3COO minus as our conjugate base. So let's start by determining the initial pH using the Henderson-Hasselbalch equation. On the previous slide, I gave you the Ka value for this weak acid. So here I've turned that into a pKa, and I've determined that the pH is going to be 4.74. Because the amounts of weak acid and conjugate base are equal, therefore the pH will equal the pKa. Now let's consider what reaction will occur. If we're adding HCl, we're essentially adding H+, so that H+ is going to react with the base component of the buffer system. Now let's think about how this is going to affect our concentrations. If we add 0.010 moles of H+, we're going to have to reduce the CH3COO- amount by that much because we're consuming it, and we're going to have to increase the CH3COOH amount because we're increasing it by that much. Plugging that back into the Henderson-Hasselbalch equation, notice that we have no change in pH because the change to this ratio is so minimal. When we take the log of that value and round to sig figs, we end up with no change in the pH. Now let's consider what happens when we add that same amount of HCl to a buffer system that has much less HA and A-. We start again by considering our initial pH, which is still going to be 4.74 because the ratio of HA and A- is still the same. Now let's consider the shift that we make. Again, we're adding 0.010 moles of H+, therefore we're going to decrease the conjugate base by that much, and we're going to increase the conjugate acid by the same amount. Plugging that into the Henderson-Hasselbalch equation, we see that we do get a significant change in pH value. So this should illustrate the point that the larger the magnitude of weak acid and conjugate base in the buffer system, the larger the buffer capacity, or the more able the system is to resist changes in pH when small amounts of acid and base are added. Now let's think about making a buffer. What things do we need to consider when making a buffer? Well, first, you want to choose an acid with a pKa equal to the pH you wish your buffer system to maintain. In other words, if you want your system to maintain a pH of 5, you want to choose an acid with a pKa of 5. If you're unable to choose an acid with a pKa exactly the value of the pH you want, it's also possible to manipulate the pH by altering the ratio of A- to HA. Recall we said earlier that if you have more A- than HA, your pH will be greater than the pKa, and if you have less A- than HA, your pH will be less than the pKa. It's also important to use large amounts of A- and HA. That will give your buffer a higher capacity. It's also interesting to note that if the A- and HA concentrations are not equal, then the buffer will have a different capacity for acid and for base. In other words, if you have more A- than HA, the buffer will have a higher capacity for acid than base, which should make sense because there's more of the base component of the buffer available to react with the acid that's added. The opposite of this is obviously also true. If you have more HA than A-, your buffer will have a higher capacity for base than for acid. So how do we practically make the buffer? Well, recall that we just said we're going to need equal-ish amounts of weak acid or base and its conjugate. I'm saying equal-ish because recall we can always shift the pH of the buffer system by manipulating the ratio of A- to HA. So there's two ways to achieve this goal. First, we could combine equal-ish amounts of the weak acid or base and its salt. So in other words, take some acetic acid, add some sodium acetate to it. That gives us weak acid and its conjugate base present in large quantities in the same solution. Or take some weak base, NH3, and add some ammonium nitrate, which will give us its conjugate acid, NH4+. The other method is to use a strong acid or base to convert about half of a weak acid or base to its conjugate. In other words, take your weak acid HF, react it with a strong base OH- to produce an equal-ish amount of F-. If you neutralize roughly half of the HF will be converted to F-, and you'll have roughly equal concentrations of HF and F-. That brings us to the end of this video. Let's review our goals. First, we looked at what a buffer system is. Recall it's a system that resists changes in pH. Then we used the Henderson-Hasselbalch equation to calculate the pH of a buffer system. Then we learned to make predictions about the buffer capacity of a system. And then we looked at how to make a buffer system.